right, so trying it again. So what I want to do with you guys really quickly is go over the last equation, basic equation for pipe flow. We were working on Monday and ran out of time with one last equation. So this quick video will go over that relationship and allow you to keep moving through homework number 10 and keep understanding better what's going on with pipe fluids that go through pipe where there's heat transfer and that heat transfers by convection. Okay, so this last relationship, the goal that we're after, is we want to relate the heat transfer to a fluid that goes through a pipe or a duct to the convective heat transfer coefficient. Okay, for the particular case where the surface temperature is constant. Okay, so pipe surface temperature is constant. If this drawing here represents a pipe, that would mean the interior surface of the pipe at all points is equal to the same temperature as you move down that pipe. All right, so backtracking just a little bit, some of our basic equations, this one right here, m dot Cp times the difference between the outlet temperature of the fluid and the inlet of the fluid, temperature of the fluid, that gives us the heat transfer to the fluid. This is a representation of what's going on. The second basic equation we had is the flux, okay? The convective heat flux. So heat might be getting out of a pipe and into a fluid by convection. It's a convection nature. And the nature of the process is convection. And this is how we would represent the flux with an equation. We're going to take our heat transfer coefficient and multiply it by the surface temperature at some point minus the mean fluid or average or bulk fluid temperature at that point. So that's last time. One thing that I should add to it, for the cases that we're going to do in this class, ME 126, we're going to do something what's called fully developed. So H is going to have the same value the whole way down the pipe. So we're just going to have a single H value down that pipe. All right, so before we try to develop this equation right here, I would just like to review constant surface temperature just a little bit. So to do that, we're going to take a look again at something similar to what we did in lecture. This would represent a pipe, and constant surface temperature would mean that at every point along the pipe, the surface temperature would be the same. I'm going to use 42 degrees C. So let's just say that this is 42 degrees C the whole way along. So 42 here, 42 there. Hang on a minute. Let me get a different pen and hopefully that'll show up a little bit better. 42 here, 42 here, 42 here, the whole way along, and also up here like this. So it would be 42 all the way along. Okay? And just a reminder how the temperature works. We're going to take a look at cases where fluids are either heated or cooled. Okay? And we started a case where, say, like a fluid came in at 14 and it went out at 40. Okay, and how is that being achieved? Well, heat is coming out of this pipe and going into the fluid. There is something else that's actually putting heat into the pipe, and the example we came up was the condensing fluid. All right, so an important reminder is to try to be able to visualize that graphically and also to think about some notation. So this x-axis represented position on the pipe. We're going to put an I here for the inlet and an O here for the outlet. And we're going to try to do two graphs on two curves on that graph. One is what the surface temperature looks like, and what the fluid temperature looks like. Okay, surface temperature is really easy. So this axis is temperature. Surface temperature is 42 the whole way along. So the surface temperature is just going to be a horizontal line. Okay, and then the fluid temperature, the bulk fluid temperature or mean fluid temperature or average fluid temperature, starts at 14 and ends at 40. So it's going to start down here at 14 and it's going to end up at 40. Okay, a couple things that are helpful to understand. First of all, I'm going to move this up a little bit. First of all, what about this thing right here? A symbol you're going to see a lot. Delta Ti. Okay, that stands for the difference between the surface temperature and the fluid temperature at the inlet. Okay, well in this case the surface is 42 and the fluid is 14. So the difference between the surface and the fluid temperature is going to be 42 minus 14. Okay, and if I'm doing my math right, that's 28. I'll move that up in just a second. So delta Ti is 42 minus 14, which is 48. Okay, you might be able to guess what this other term is going to be. I'll move the board in just a second. Delta TO. Delta TO, what's that going to be? That's going to be the difference between the fluid temperature at the surface temperature at the outlet and the fluid temperature at the outlet. And that's easy enough. Surface 42, fluid 40, so in this case delta TO is 2. Okay, so our delta T, where delta in this case means difference as opposed to change, varies from 28 to 2. And you can see that graphically. We have a big temperature difference here, a small temperature difference there. Last thing is, hey, what does this curve look like that would represent the fluid's temperature as it goes through that pipe? Well, again, it's happening by convection, and convection is driven by delta T. We have a big delta T here, a small delta T here. We're going to get a lot of heat transfer at the beginning of the pipe and less down at the end. So the fluid is going to rise quickly at first, and this rise is going to become less steep as you go along. All right, so that's where we left off. And now let's get back to this question about how we're going to relate the heat transfer to the fluid, which can be calculated using this equation here, to our H value, our convective heat transfer coefficient. So give me a second to erase the whiteboard, and we'll get at it. What we just need to do is write down the equations that we had, and then one more basic idea. So let me get those up there. Heat transfer to a fluid is going, if it goes through a pipe section, is going to be m dot Cp times delta T, where that is the change in temperature of the fluid. Okay. Our flux at any point is going to be given by our H value times the surface temperature at that point minus the mean fluid temperature. Okay. That's the second relation that we're going to have. Okay. And then finally, pardon me, give me just a second. We can, in addition, think about the definition of flux. Okay. So flux, in any situation, is heat transfer divided by area. Okay. And we're almost there. I'm just going to rearrange this equation to say that heat transfer is flux times area. Where in this equation here, this represents the surface area of the interior of the pipe. All right, well, it's easy enough to see what we wanted to do was relate this term here to H, okay? And what you can do is you can see, well, this is flux right here, and maybe we could plug it in for flux right there and get a valid equation that we can use. And that's almost close to correct. Oh, go ahead and write that. Okay, sorry about this line going through there, but this would be a really easy and convenient equation to use. H we were going to know. For a pipe, we're either going to know its interior surface area or we can solve for it. But what are we going to use for this term right here? And that's the surface temperature minus the mean fluid temperature. Okay, well, let me write some numbers up there for the previous example that was on the board. Ts minus Tm. What might we use for that case? Okay, 28, 2, or 15. So I just want you to think about it. What do those numbers represent, and what might be which one might be best? Okay, well, 28 was the difference at the inlet. I'll just go ahead and draw that up there. We had water coming in at 14 degrees C, and our pipe surface temperature was 42. I'm just going to draw the bottom part of the pipe where this was 42. Okay, how about 2? What did that represent? That represented the surface temperature at the outlet, where the water's coming out at 40. Okay, and what would 15 be? Well, 15 is a really good guess. It would say, look, the appropriate thing to do to get the average flux, which I should have said this is here, this flux should be the average flux, okay, would be to use the average temperature. Okay. The problem from what we saw earlier is that this 28 degree temperature difference here, 14 minus 42, doesn't last very long. So the temperature difference of 28 only lasts for a short section of the pipe, and the rest of the time the temperature is less, difference is smaller. So 15 would be an overestimate of the average temperature difference. So we're going to use this equation, but we're going to specify what temperature difference we're going to have, and that's going to be essentially the effective average temperature difference. So let me write that equation down there, and then we'll tell you how you're actually going to work that out. So essentially what we're going to do if we're relating Q fluid and H is we're going to take the H value, we're going to multiply it by what I could put as Ts minus Tm effective, and don't write that down, I just want you to think about it, times the surface area. Okay, where in the previous example that we did, this is not going to be 28, that was at the inlet. It's not going to be the 2, which was at the outlet. It's going to be somewhere in between 28 and 2, but it's going to be closer to 2. Okay. All right. So it would be great if we could go through the derivation of how to get the effective average temperature difference between the surface and the mean fluid temperature, but I'm just going to go ahead and give you the formula. It comes from calculus. It's not that hard to do. Okay. And give me just a second, please. It is called the log mean temperature difference. So many times it's abbreviated as LMTD. Stands for essentially the mean temperature difference between the surface and the fluid if you have a fluid going through a pipe and that fluid surface temperature difference is not constant. And the way you calculate it is you take the difference in temperature between the fluid and the surface at the outlet minus the difference in temperature between the fluid and surface at the inlet, and then you divide it by the natural log of the difference in the temperature in the outlet minus divided by the difference temperature of the inlet. Okay, and that's a very important formula. Okay, we're going to use that quite a bit, and if you do any sort of work with heat exchangers, okay, or with pipe flow with constant surface temperature, you're going to use that a lot. All right, so first thing is just go ahead and pull out our calculators and let's actually work through that for the numbers that we just had. So I'll just make it a quick example. Okay, I've got a pipe, got a fluid going through the pipe. The surface temperature of the pipe all the way along is 42 degrees C. Okay, and then the fluid comes in at 14 and goes out at 40. What is the effective temperature difference for heat transfer between this fluid that's going through there and that surface? Okay, we're just going to plug and chug and go through it. I'll start getting the numbers up there. Encourage you to do it on your calculator and see if you get the same thing. So, delta TO, 42 minus 40, the temperature difference at the outlet, delta TO, that's 2. Okay. Delta TI, the temperature difference at the inlet, 42 minus 14, that's 28. This is looking weird. It's looking like we're going to get a negative number. We should get a positive number because the surface temperature is hotter than the fluid temperature. But we still have to do the denominator. So natural log delta TO, 28, divided by delta TI, which is 2. Whoops. Okay, and then it's time to take a break from just looking at the whiteboard. Pull out your calculator and give it a try. I'll do it myself and we'll see if we get the same numbers. Actually, can you hang on for just a second, please? Hopefully some of you guys caught it. I mixed up the denominator. So the denominator should be delta TO over delta TI. So that should be LN2 is the outlet temperature difference, and 28 is the inlet temperature difference. Sorry about that. Maybe make that change. Okay, so my calculator gave me 9.85 degrees C. That's a positive number, 9.85 degrees C, and that makes some sense. We were saying that we had a temperature difference of 28 over here, 2 over here. The average between that is about 15 degrees, but This big temperature difference does not last for very long in the pipe, and pretty soon we get down to a small temperature difference. So there it is. So it's 9.85. All right, well then that's it. That log mean temperature difference then allows us to relate the heat transfer to the fluid, okay, to the H value. And the book just writes it in a different order where they put the surface area here like this. So your equation for this case is the heat transfer to the fluid is equal to H, the H value, times the surface area of the pipe, the interior surface area of the pipe, multiplied by the log mean temperature difference. And I'm going to do a different symbol that is used sometimes in the book. I should have gotten that up there. The log mean temperature difference is sometimes denoted delta TLM. Okay, so let me go ahead and box that. Okay, so you're good to go. Most of homework number 10 is then practicing with these various formulas. There really is no set technique. First you do this formula, then you do that formula, then you do the other. You just have to get a little bit of experience thinking. And so I encourage you when you do that homework to have the various equations lined up and maybe some diagrams and concepts to help you visualize what those equations are saying and work through that. All right, very good. That is it.